Welcome to Science Coat NEET, where chemistry isn't just memorized, it's lived. In today's episode, we'll take you on a creative journey through Hydrocarbon City, where every bond, reaction, and molecule has a story. Let's make learning fun. And hey, don't forget to subscribe and drop a comment if you love these audio stories.
Welcome to the deep dive. Today, we're taking you on a really unique journey. Think of it as a shortcut to getting your head around some core organic chemistry. We're calling it Hydrocarbon City, the land of bonds and reactions. Our mission here is simple. We've got this great narrative source material, tells it like a story, right? We want to pull out the key bits about hydrocarbons, make this dense topic, well, approachable, memorable even.
Absolutely. And, understanding hydrocarbons is just so crucial. They really are the fundamental building blocks for, well, so much of our world. Think energy, plastics, medicines. It's all built on this stuff. And the city idea, it's not just for fun. It genuinely helps you visualize how these molecules are different, why they act the way they do. It connects the what to the why and the how.
Okay, let's dive in then. First stop on our tour, Alkane Nagar. The source calls it the most peaceful suburb. And the defining thing here, all the connections, the bonds between carbons are single bonds. Simple, right? And you probably know the naming. Names end in alkane. Like methane, ethane, propane, butane, pentane. Depends on the number of carbons. But even though they sound simple, these single-bonded molecules aren't totally rigid, are they? There's more going on.
Oh, definitely not rigid. That's a really key point. Even with just single bonds, these molecules can twist and turn. We call these different shapes conformations. They can rotate around those single bonds without breaking anything. The source mentions two ways to draw these, Sawhorse and Newman projections. The Newman one is especially good for seeing this rotation. It lets us figure out, which shape is more stable, uses less energy. It's all about molecular flexibility.
Flexibility. So even in this peaceful suburb, things can happen. The source mentions a character, the halogen uncle, showing up. What kind of reaction does this uncle kick off in Alkane Nagar?
Right, the halogen uncle. This introduces a really important reaction type, free radical halogenation. Free radical means it involves these super reactive bits with unpaired electrons, and it's very systematic. It happens in 3 clear steps: initiation, getting it started; propagation, keeping it going; and termination, stopping the chain. It's a great example of how chemists can predict and even control what happens in a reaction. Very orderly, like the source implies.
That predictability is definitely a feature of alkanes.
So thinking about this ordered world of Alkane Nagar, what really stands out to you about how these seemingly full molecules react? Okay, moving on. Let's leave the quiet suburbs and head to Alkane Street. The source labels this the double trouble zone. Why? Because here we find carbon double bonds, 2 lines connecting them, and the names change too, right? Now they end in -dene, alkene. Exactly. Oh, and butene. And that double bond, it brings a lot more than just trouble. It brings possibilities. One big thing is geometrical isomerism. The source has this nice description. Cis and trans forms as twins that are the same but upside down. And unlike single bonds that can freely rotate, that double bond is rigid. It's locked. So cis and trans aren't just different views, they are truly different molecules. Different shapes, different properties. It matters a lot, especially in biology.
Okay, so that block creates distinct forms.
Yeah.
Now, these double bonds are rich in electrons. What kind of things are attracted to Alkane Street? Who are the favorite guests?
Good question. The favorite guests are electrophiles. The name literally means electron lovers. Makes sense, right? They're drawn to that electron-rich double bond. Take HBr, hydrogen bromide, a common electrophile. When it adds to an alkene, it usually follows the Markovnikov rule. Basically, the rich get richer, the hydrogen adds to the carbon that already has more hydrogens.
Okay, Markovnikov rule.
Yeah.
Got it.
But, and this is really cool, if you add peroxide to the mix, everything flips. You get the opposite outcome. We call it anti-Markovnikov addition. The hydrogen goes to the other carbon.
Wow, just one extra ingredient changes the whole result?
Exactly. It shows how chemists can steer reactions. It's like having molecular control, directing where things attach. Really powerful for synthesis.
That is powerful.
Yeah.
Almost like molecular architecture. Are there limits to that control in the real world, though? And besides HBr, Alkane Street is busy. The source mentions other nonstop reactions. Hydration, halogenation, and ozonolysis. What's the common thread there?
Well, many of them are addition reactions. That double bond essentially opens up, and new atoms or groups get added right across it. Like hydration adds water, halogenation adds halogens. Ozonolysis is a bit different. It actually cuts the double bond in 2.
Yeah.
Super useful for figuring out structures or building new molecules. Basically, that double bond is a reactive hotspot. It invites these transformations.
It's fascinating how just Changing from a single to a double bond opens up so many new reaction pathways, isn't it?
Uh,
All right, let's keep moving. We're climbing now up to alkyne hills.
Huh.
This is where the triple bond ones live. 3 bonds connecting carbons.
yeah, the alkynes. And that extra bond, that third bond, gives them a really unique property, especially the ones at the end of a chain. They have an acidic nature. The source says they can give H plus B.
Hang on, acidic. Hydrocarbons aren't usually acidic, are they?
No, they're generally not. That's what makes alkynes special. That triple bond pulls electrons in such a way that the hydrogen attached to it is, well, surprisingly easy to remove as H++ boat. It's not super acidic like, say, sulfuric acid, but acidic enough to react in ways alkanes and alkanes just can't. It opens up unique reaction pathways.
Okay, so they have this unique acidic personality. What kinds of reactions do we see happening up in alkene hills then?
Well, like alkenes, they undergo addition. Hydrogenation is a key one. You can add hydrogen step by step. Add one molecule of H, you get an alkene. Add another, you go all the way down to an alkene. You can often control how far you go.
So you could choose your product, alkene or alkene.
To an extent, yes, with the right conditions. And things like halogens and HX, like HBr again, also add. But here's the key difference. Because there's a triple bond, they can add 2 times. You can add 2 molecules of HBr across the triple bond, for example.
Ah, double the addition potential compared to an alkene.
Exactly. More bonds to react with.
So as you think about this progression, single, double, triple bonds, what's the biggest takeaway for you about how that third bond really changes the game for a molecule's potential?
Okay, final destination on our tour. We've arrived at the grandest part of the city, Aromatic Chalk. Our source calls it the Royal Circle, and it's ruled by the king benzene. It's got this very specific structure, a 6-carbon ring, but it's not just alternating single and double bonds, is it? There's something special. Electron clouds of delocalization. Sounds fancy. It is special. That delocalization is everything for benzene. Those electrons aren't stuck between just 2 carbons like in an alkene. They're shared, smeared out over the entire ring. Think of it like a continuous loop of electrons above and below the ring. And this sharing, this delocalization, makes benzene incredibly stable. Much more stable than you'd expect if it just had 3 normal double bonds.
Okay, so super stable because the electrons are shared all around.
Yeah.
How does that affect its reactions? Does it do the addition reactions we saw with alkenes?
Generally, no. That's the crucial point. Addition reactions would break up that stable delocalized system, and benzene doesn't like that. Instead, its signature reaction type is electrophilic substitution.
Substitution, not addition, so swapping something out.
Exactly. An electrophile comes in, and instead of adding across a double bond, it replaces one of the hydrogen atoms on the ring. The stable aromatic ring stays intact.
Makes sense. So what are the common examples? The source lists a royal court of reactions.
Right. The classics are halogenation, adding a halogen like Bre or Cl, nitration, adding amide allo, and sulfonation, adding allos, and the Friedel-Crafts reactions, both alkylation, adding a carbon group, and acylation, adding an acyl group, CeLO. These all follow that substitution pattern, keeping the aromatic ring happy.
Okay, but then the source mentions something even more specific. Directive functional groups. What's that about? Sounds like they give direction.
They absolutely do. This is where benzene chemistry gets really elegant, really strategic. If there's already a group attached to the benzene ring, it influences where the next electrophile will attack. It directs the substitution.
Like a traffic cop on the ring.
Sort of. Some groups, like OAH, hydroxyl, or haseose, methyl, are orthopara directors. They steer the next group to the positions right next door, ortho, or directly across the ring.
Okay, ortho and para.
Then there are other groups like net-OARO, nitro, or net-OACuOH, carboxylic acid, which are meta-directors. They steer the incoming group to the position that's 1 carbon further away, meta.
So different groups send the next attacker to different spots.
Precisely. And understanding this directive influence is incredibly powerful for synthesis. It allows chemists to build complex molecules with specific structures by adding groups in a controlled sequence. You're not just getting a random mix, you're guiding the reaction.
That level of control is amazing. It's not just random chemistry, it's planned, like molecular engineering. And that brings our tour of Hydrocarbon City to a close. What a journey. It's definitely not a boring place, is it? Hopefully, seeing it this way, like neighborhoods with different rules, helps make sense of it all. Understanding these stories of chemistry, the fun of reactions, really can make these complex ideas click.
I absolutely agree. I think the main thing to take away from this deep dive is how fundamental the bonding is. single, double, triple, or that special aromatic delocalization, that core structure dictates almost everything else. The shape, the stability, the reactions the molecule will undergo. What still surprises me sometimes is just how much chemical diversity and utility comes from these seemingly small changes in bonding. Fuels, plastics, drugs, all built on these principles. This kind of structured, metaphorical approach really helps you grasp both the big picture and the crucial details.
Definitely. So as we wrap up, here's something for you, our listener, to think about. We just heard how functional groups can act like directors, guiding reactions on a benzene ring. Where else might similar ideas of molecular guidance or recognition be playing out? Could it be in biology, like how enzymes latch onto specific molecules? Or maybe even in how scientists design new smart materials? How far do these fundamental principles of molecular interaction really reach? Something to ponder. Thanks for joining us on the Deep Dive.
That was your tour of Hydrocarbon City, where the magic of chemistry comes alive with every reaction. Stay tuned with Science Coat NEET for more science-packed stories and neat concepts made simple. Like, comment, and subscribe, and as always, learn, apply, and thrive.